Dynamic programming is the name of the game. Dynamic programming is called dynamic programming. I don't even know where it got us from its name. It probably just sounded cool, and the person invented it who decided to call it that, just to sound cool. But all dynamic programming is breaking up a problem into smaller and smaller bits. So if you have like a huge problem, you can break it into smaller subchunks, and then put them all back together at the end. Yes, if you say so. So let's say we start with a very simple recursive Fibonacci sequence program. I'll be writing this in Python because it's just this because Python is the same thing as pseudocode. Let's call this one Fibonacci. Let's call it a Fibonacci. Let's give it a number. And then obviously the base case would be, it'll look something like this, right? 1, 1. Sorry. Does it start at 0 or 1? 0, 1, 1, 2, 3, 5, 8. This starts at 0, right? So if... Okay, I'll just start at 0. So... Right, CS class starts at 0. So obviously, the base case for this recursion would be, if the in is less than 2, then I'm just going to return in. Because if it's 0, I'm going to return 0. If it's 1, I'm going to return 1. Return in. And then obviously the Fibonacci sequence is defined by the sum of the previous two indexes, or the previous two elements. So it'd just be return Fibonacci of in minus 1 plus the Fibonacci of in minus 2, right? So if I call Fibonacci of 3 is going to be Fibonacci of 2 plus Fibonacci of 1, which is Fibonacci, oops, that's a D. That's an F. How do you do a B? Oh, that's a D. That's a B. Fibonacci of 1 plus Fibonacci of 0 plus another 1, which obviously would be Fibonacci of 1 and 1 are 1 plus 0 plus 1 equals 2. And 3 goes to 2 over here. Same thing with 4. 4 would go to 3, 5 would go to 5, 6 would go to 8. Let's code this one. I'll just define the Fibonacci sequence as if in is less than 2, then I'm just going to return in. Otherwise, I'm going to return the Fibonacci of in minus 1 plus the Fibonacci of in minus 2. And then let's just do a while, let's do print Fibonacci of the input, and we'll just run this one. Do the cd, run this Fibonacci file. I'm just going to do a Fibonacci of 0, as expected, that's a 0, 1, 2, 3, 4, 5, 6. That's all fine. 10, 55, 20. That's a big number. Let's do 100. That's not good. That's taken a very long time. Let's go this one. Let's go back to like... let's go back to 30. Even 30 takes a long time. Let's try 31, 32, 35. Could do a funny. Yeah, even 35 takes a long time. The reason that's so slow is not just because Python is slow. It would run slow even if you made it in another language. Even if you do it in C++, that'll also be the same speed. The problem here is that, yeah, Fibonacci 35, that took like 10 seconds already. Every time we do Fibonacci of 35, I'm just do a 35 instead of the fib, just to save space. 35 is splitting up into 34 and 33. And if we split that further, that's just going to be a 33, 32, 32, and 31. And each of these ones are just going to keep splitting over and over again. Yeah, you get the idea with these ones. And the problem here is that there's so many things that are repeated. Every time I call 33, That's going to be the same thing every time. I don't need to keep calling 33 again over here if I've already calculated it before. So if I calculate Fibonacci of, let's say 32, then this is going to be the same thing, and this is going to be the same thing. I don't even have to recurse further if I've already calculated those. So I can just, every time I call Fibonacci, I can store the result in a lookup table. Let's say our lookup table looks like this. I'm going to call this, it's just going to be a regular array. 0, 1, 2, 3, these are all the indexes, right? Let's say I call Fibonacci of 4. When I call Fibonacci of 4, I'm going to call Fibonacci of 3 and 2. 2, 1, 1 and 0. And so Fibonacci 4 is going to split into these three. And when I call 2, I'm going to call into Fibonacci of 1 and 0. And these are just the base cases, obviously, 0. So these are just obviously the same values, because I defined the base case as if the number is less than 2, if it's 1 or 0, it'll just return the same number. But let's say we get to 2. When I get to 2, Fibonacci of 2, every time I call Fibonacci 2, it's going to return the same number every time, which is going to be 1 plus 0. So instead of having to calculate Fibonacci of 1 plus Fibonacci of 0, I can just calculate Fibonacci of 2 once. The first time I call Fibonacci of 2, I'm going to store it in this table. I'm going to store the result in this table. I'm going to call this one 1. Subsequent times, so this one is complete. I'm calling Fibonacci of 2 over here as well. I go to the table and I see there's something in the table. There's a 1 in the table. So instead of recursing further, going to Fibonacci 1 and 0, I can just pull this value from the table and directly return this, instead of having to recurse further through 1 and 0. Same story goes for 3. Obviously, it doesn't seem like very much here, just because there are so few elements, but it'll be a huge improvement once we make the lookup table for this 35. So I'm just going to change the code. It's going to be a very, very simple change. I am going to first push all of this stuff downwards. How do I use the mouse? Oh wow, look at that. Let's see. Scroll. How do I scroll? There we go. So I'm going to do one line of code that's above this. And I'm going to do something like this, actually. I'm going to do like this. I'm going to erase this one, and I'm going to say, if a lookup at in is not -1, and I'm going to set -1 as like the default value of the lookup table. That means that there's no value stored in there yet. Then I'm just going to return the value directly from the lookup table. Return lookup at in. Otherwise, I'm going to calculate it. I'm going to set the result. I'm going to make a new variable this time. Result equals Fibonacci of in minus 1 plus Fibonacci of in minus 2. And I'm going to set lookup at in to the result, and then return the result. Just like that. That's like what? 2 new lines of code? Well, this one, yeah, 2 new lines of code. This one, res, and return res is the same thing. But yeah, just making 2 lines of code. Of course, we have to actually make the lookup table beforehand. Let's make a lookup table equals, and I'm going to set this to array of, let's make this one 1,000 characters, 1,000 numbers. Or maybe just 100 for now. I think the Python syntax is like -1 for, let's call this one 101. So our Fibonacci can go up to 100. Okay. Let's call this one. I'm going to start with the lookup table. I can't actually remember the Python syntax for tables. I think it's this. So that's going to make a new array of length 101, which is going to give us indexes 0 to 100. Let's give this one a try again. Of course, the code. And then I'm going to see if lookup at in is not equals to -1. Let's give this one a try. I'm going to modify the code a little bit as well, just to make the output a little bit cleaner. Just going to format this more. Oh, let's do. Fibonacci of in. And then I'm going to print the formatted string of. Okay, let's give this a try again. Just like before, obviously, if I type in 0, it'll be 0. If I type in 1, it'll be 1. 2, 3, 5. You get that idea? What happens if I type in 35 now? That's instant! See how fast that was? Since it wasn't calculating each of those numbers one by one, it was calculating only once and then storing it into the table. Let's do something like this, actually. Okay. Let's do a tin. Then it's going to set the lookup table to the values. I'm going to see when it's going to access the lookup table as well. Let's do it like this. Let's say Fibonacci of 2, set lookup 2. What if I do 2 again? Even if I do 2 again, even in between the times I call the Fibonacci, it's going to look at the lookup table instead of running that calculation because it's already in the table. So that's stored in between calls of Fibonacci. If I type in 10, look how many times it's accessing it instead of having to calculate it by itself. If I type in 10 again, it's just going to access lookup 10 instead of running the same calculation. Let's do 100. Well, that's a big number, but see how fast that was? Still the same speed? 200. Uh-oh. Oh, right, because the table's only 101. That's the simplest version of the dynamic programming with a lookup table. There's also one other way to do this using the hash map, which I will go over in the Collatz problem. So you guys have seen the Collatz, right? If the number is odd, then it would go to 3 times the number plus 1. But if it's even, it'll go to the number divided by 2. So let's just make that a function. Collatz of in. And I'm going to do if in, let's see. If it has a remainder, then I'm going to return 3 times in plus 1. Else, return in divided by 2. I'm trying to find out the starting number that produces the longest callout sequence. This is Project Euler problem 14. So I think it's 1 million numbers. So I'm going to run the callout sequence for numbers under 1 million and see which one produces the longest chain. So I'm just going to do a simple for loop for in range. Is that a million? It's 10,000. I'm going to do maximum number. I'm going to start it out as 0. And the max chain is also going to be 0. I'm going to see. Oops, that didn't happen. I'm just going to make one more called the Collatz length. Kind of like before, I'm just going to run the Collatz sequence until I get to 0. I'm going to set the count to 0. That's the number of moves. I'm going to do while in is greater than 1, because it's always going to end up at 1. I'm going to do in equals Collatz of in, and I'm going to increase the count. And then I'm going to return the count, and that'll give us the length. I'm going to set this, let's do like this. Length equals len Collatz of in, and I'm going to do, let's see, what is this one? I'm going to do if the length is bigger than the max length. I'm going to do 2 things. I'm going to set the max to in, and I'm also going to set the max length to length. And then I'm just going to print out the max length. Python Collatz. That's going to take a long time. Let's try this again with a smaller number. Longest chain, or let's see. Oh, let's print out the max instead of the max length. The number 9 is going to give us the longest chain, starting at with a length of 19. If I go, that would be 9 to 28. Let's see. Let's put it down here. 9, 28, 14, 7, 22, 11, 34, 17, 52, 26, 13, I think I'm doing this right, 40, 20, 10, 5, 16, 8, 4, 2, 1. That's a long chain, yeah. So let's say I'm doing that again. And so the Collatz sequence has a lot of repeated numbers as well, kind of like before with the Fibonacci. It has the same concept of if I calculated one thing, that's going to be the exact same thing every time, so I don't need to calculate it again. Fibonacci of, let's get a Fibonacci of 40. Let's say we calculate Fibonacci 40 ahead of time. Fibonacci of 40 is always going to be the same thing every time, which is going to be 40, 20, 10, 5, 16, 8, 4, 2, 1, which is going to give us a length of 9. So we can store this Fibonacci of 40 inside a lookup table as well. In this case, though, let's use a hash map instead. A hash map is just a simple map that maps a key to a value. All the keys are unique, values don't have to be. In this case, I'm going to map the key is going to be our starting number, and our value is going to be how many moves it took. Let's do that over here. So 10 is fine, but we saw that 1 million took a hot minute. I'm going to call this one the, before we used the lookup table, let's call this one the cache. It's a cache with an H. Okay. And I'm going to do like this. We're going to do okay. I had to change a few things there. Yeah, there we go. Big number. So something was wrong with my logic before, but all this one is that I'm seeing. I'm going to run the Collatz sequence on here, and I'm going to see if the next number, is already in the cache. I'm just going to access the cache plus the count. Since the cache is going to store the number of the Collatz sequence along with how many moves that number will take. So our cache might end up looking like this. If I call on the range of 5, let's say Collatz 1, Collatz 2, Collatz 3, Collatz 4, and Collatz 5. And that's going to be like this. Let's call it Collatz, yeah, I'll start at 5. I'll stop at 5. Our hash map is just going to look like this. 1 is going to have a length of 0. Our 2 is going to have a length of 1. I'm going to have to run the Collatz sequence, 2, 1. I'm going to see 1's already in the cache, so I'm just going to pull the 1 here, which is 0, which doesn't make an impact on performance. But once we get to 3, 3 is going to be 3 plus, so 3 is going to be 3, 10, 5, 16, 4, 2, 1, which is going to give us a length of 7, right? Because that's 7 elements of that sequence. A 4 is going to give us a sequence of 3, because 4, 2, 1. Or 5, here's where it gets interesting. 5 is going to go 5, 16, 8, 4. Hey! 4's in the cache. I don't need to keep calculating further. I could just add on the current count, which is 3, plus how many 4 will take, and 4 is going to have 3. At 4 equals 3 plus 3, which is going to be 6. So 5 is going to take 6. I'm not going to keep calculating further after 4. I'm just going to see if the 4 is in the cache. If it is, I'm just going to take the 3 out and use that 3 instead of calculating further. Oh, scuffed. Oh, got its work. And apply that to bigger numbers as well. That'll still be much faster than what it was before. If I leave out the cache, I think the time for this one to run would be around a minute. So I'm just gonna remove this one. Let's see how long this one takes. And I'm just gonna leave this to run while we work on the palindrome. Now the palindrome is interesting. The palindrome is more of a recursive one. It's kind of like a recursive dynamic programming. This problem goes like this. I'm gonna give you a string. Let's give you a string of what's a good string to use? Kayak. Obviously that's a palindrome, right? Because it's the same thing reversed forward and backwards. And we're given a string that's not necessarily a palindrome. Let's say we have something like A, B, A. And we have to find the least amount of moves it will take to turn this string into a palindrome. A move is defined as adding a character, deleting a character, or what's the third one? Changing a character. Let's see. So let's take this string of AABA. Well, so AABA. Let's take a look at just the first 2 letters. First 2 letters is an A, or the first letter and the last letter. A and an A. So right now so those 2 are equal. So I'm just gonna call. Let's put this in a function. Def palin to jazz. Oh, interesting. Let's see, palindrome of S. I'm gonna see if the string at 0, if the first character is equal to the last character. This is how it's done in Python, because Python is silly like that. And I'm just gonna return. Here's what's gonna get interesting. Palin. I'm just gonna return the function with the string with the first and last character cut off. 1, 2, -1. So if the first 2 characters are equal, I'm just gonna do A, B. So it gets interesting here because the first character it's not a palindrome, right? I have to say what's more efficient. Is it fine to add a character, delete a character, or change a character? In this case, it's completely fine to do either one of these. We can either add a character here to make it a palindrome with only 1 move. You can delete the character B to make it a palindrome with only 1 move. Or you can change this B to an A. Or you can change the A to a B. That's only 1 move as well to make it a palindrome. But we want to see the minimum number of moves for any type of string. Let's say we have a more complicated string. I'll go away, ruler. Let's say we have a string that's like... It's a complicated one I could use. A, B, C, A, B. Not a real word. But the optimal solution for this one, would it be to change this character here to a B? Or would it be to... If I change this to a B, 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 C, A, B. That's fine. That'll just go to B, C, A. Then I don't have to worry about this string. What's better for this one, you can also, so we have like many different options here. Let's start with each of the options. Let's start by adding a character, deleting a character, or changing a character. We can add a character to the optimal character to add would either be a B on the left side, that'd be B, A, B, C, A, B, or you can add an A to the right side. We want to add the same character to both sides, that way those characters can cancel. Or you can do A, B, C, A, B, A. That's just adding a character. You can delete a character by doing... Okay, let's not worry about the deleting character. Just two cases. Deleting a character and changing a character. I don't entirely remember this problem, so it's hard. If you would change a character, you can either change... You can change the A to a B by doing a B, B, C, A, B. Or you can change this B to an A for A, B, C, A, A. In this case, it would just go to A, B, C, A. In this case, it would be B, C, A, B, and then B, C, A, and then B, C, A. Looks like these two are the exact same. Why change the character there? Because changing the character at the left or that side, all it's going to do is reduce it because you're removing one character. If I change the character here, that'll be immediately removed because these two characters would be the same, so these would be crossed out. If I change the character, because our starting string was like the A, B, C, A, B. If I change the first character to a B, these would be immediately cancelled. If I change the last character to an A, the same result, it would just be immediately cancelled. In both cases, changing the character is just going to remove the last two characters and then add one to the moves. In these cases, it's going to remove one of our characters, either the character from, if our original string was A, B, C, A, B, you can either remove the string, you can either remove the last character or remove the first character. And now I'm going to group these two into one. Oops. Because these are going to be the same thing every time. Changing a character is just going to result in the same thing. And I have to see which is the best out of these three. And just like before, I'm going to call the palin on this one. And it's just a simple recursion. I'm going to add all those moves together and see the minimum number of moves. I'll move this one over here for now. And I'm going to see something like this. Oops. Return the minimum of palin. I'm going to start with the change, with the add case. In this case, I'm going to add one character to the left side, which is the same thing, since adding a character to the left side is the same thing as removing a character from the right side. So that would just be a string start at 0 and just go to -1. Next case, it would be the palindrome of adding a character to the right side, which is the same thing as the substring past the first character. Just be like this thing. Palindrome of the S1 to the end. And the very last case, it would be changing a character, which just means removing a character from both sides. And I'm going to plus 1 because it takes one move over here. Although this doesn't have a cache or a lookup table like we used before, this is still a form of dynamic programming because we're splitting up one big problem our big string into many, many subproblems. And that's all that dynamic programming is. You have a big problem, and you split it into smaller pieces that are easier to calculate. Like the sum of those parts is going to take less time to calculate than the calculating the huge string. Let's give this one a try. If s at 0 equals s at last, return 1 plus the minimum of, since minimum we're looking for the least number of moves, palin of the string. That's going to be, I know the syntax is weird if you guys haven't seen Python before. All this s colon -1 means is that if we have a string abcab, the first thing here, I leave this one blank. You can think of this one as a 0. If it's blank, on the first one it's going to be 0. It's like a substring, or like a, yeah, substring. I'm going to start at index 0, and I'm going to, and the ending index is an index, the length of the string, minus 1. So the length of the string is 5, and I'm going to go to minus 1, which is 4. But we don't actually include the 4. So really it'd just be a substring of 0, 1, 2, and 3. 0, 1, 2, and 3. It would be this thing. If I did s of 1 colon nothing, you can think of this one as starting at 1 and going to the length of the string, which is b4, this substring at the very end. And if I combine those two, s1 colon -1, it'll just be this middle sub over here. That's what I'm doing over here. Minimum of the palindrome of s-1, palin of s1 colon, and palin of 1 colon -1. Palin. And obviously, if the length of the string is less than 2, then it's guaranteed to be a palindrome. We're just going to return 0. Because any string that's blank, or any string that's just one character, has to be a palindrome. Let's start with a palindrome of, well, let's just like print all the inputs. Let's give this one a try. Python palindrome. Let's give it a simple string of a b should be 1. Let's give that one a try with a big one. A b c a b. 2. The optimum number of moves we can use is 2. Oops, that's the background. Optimal numbers of moves we can use is 2. In this case, this change is not optimal because it would leave us with 3 different characters. But if we keep going with the add, the b, we would end up with a abca or a bcab, which would be just a bc or a ca. And in this case, the best thing to do would just be change a character, either the c to you can change the c to a b, the b to a c, or you can just add a b over here. Just like before, CAC or ACA, CC or AA. So we're going to get the minimum number of that. Because splitting the big problem into smaller problems. How about a case where it's better to change than to add a character? I'm going to think about that. Let's just do A, B, C, D, E, F. That's going to be a long one. In this case, the optimal result wouldn't be to add a character to each side. If I add a character to, let's say I keep adding the same character to the right side. 0 moves here. It'll take 1 move to change that into A, B, C, D, E, F, A, which is a B, C, D, E, F. 2 moves to go to B, C, D, E, F, B, or C, D, E, F. And then same pattern repeats, 3, D, E, F, 4, E, F. and then a 5 would just be the palindrome by changing that to an, let's say, a EE. Sure. This is an F. Yeah. 5 moves by just adding the character to each side. But if I change this F to an A, it'll just be A, B, C, D, E, A. That'll take 1 move, or B, C, D, E. If I change the E to a B, that'll turn out to be C, D. And that'll take us 3 moves. So in this case, it'd be better to change a character instead of just adding characters. And this program accounts for that as well, because I'm using the minimum. I'm taking the minimum number of moves I can get to that ending character, to the ending palindrome. So if I type in A, B, C, D, E, F, it should return a 3. Yeah,